Hello and welcome to another lecture of classical motion of a single particle. In this lecture, I will just deviate from our previous discussions a bit and somehow start a new topic. I mean, it is not in a sense new topic, but which could have been discussed much earlier when I already discussed or introduced the Newton's laws of motion. If you remember, I have introduced just the first two laws of Newton, okay, and I did not talk about the third law yet. So, really right from the first law, what I said that the meaning of the first law is to give a qualitative definition of force, how the dynamics comes into play in the realm of classical mechanics. So, and there we actually saw that qualitatively force can be understood as an external entity by virtue of which you can always try to change the state of motion of a particle. So, if a particle is at rest, then the particle will be at rest if you do not apply a force. If a particle is at constant motion, that means is moving with a uniform velocity, then again if you do not apply any external force, the particle will move always with the same uniform velocity. Okay. However, if you apply a force which is non-zero, then the particle will accelerate or decelerate, and that is given by the ddt of its velocity. Okay. It can be positive or negative. But if you have also the action of more than one forces, then of course you can have a situation where the net force may or may not be 0. If the net force is 0, again you will have a 0 net acceleration or deceleration, thereby giving you the condition for equilibrium. If you have a non-equilibrium condition, then that means the sum of the forces, the vector sum of the forces is not 0, then you can actually say that okay, there will be a resultant acceleration or deceleration. Okay. And if you now say that okay, if I am just thinking a particle which is changing its mass, then it is not always necessary to have an external force to have a non-zero acceleration. That also we have seen in one of the exercises. Okay. Now, in this lecture, what I will again start a little bit from 0, that is the Newton's first law. So, Newton's first law said that unless you force a system from exterior, there will be no change in the state of motion. Okay. That means rest will be rest, uniform motion will be uniform motion. Okay. Now, the point which we somehow omitted is that when we are saying that some particle is at rest, some particle is in uniform motion, that means is moving with uniform velocity, someone has to conclude about the state of the motion. Okay. And that someone is called an observer. So, who observes the motion and who concludes. So, observer observes the motion or the state of motion and concludes. Okay. But an observer can actually, so for example, many a times an observer is simply a human being or any living organism, okay, who can see, okay, who can watch. Okay. Now, the point is, although the observer may conclude qualitatively, in order to have a quantitative conclusion, the observer needs some way to measure things. For example, if the observer says that the particle has moved by a distance of 5 meters, then the observer needs some scale or some measuring instrument to measure the distance. Also, if the observer wants to measure the time, so that the observer can say that okay, in this time interval, let us say 3 seconds, the particle has moved by 5 meter in order to calculate the velocity, then also the observer needs a clock, okay, to measure the time. So, in general for measuring the distance, what we use? We use a scale, and more generally we can say we use actually a coordinate system. Okay. So, basically coordinate systems are the combination of scales at different independent directions, okay, that you all know. Okay. So, the coordinate system to measure the distances, and a clock or a timer. Okay. Okay. So, that is to measure the time, or that measure the time interval, to be precise. Okay. If you have the combination of these three, then we can define what we call a frame of reference. So, a frame of reference means you have an observer which or who is sitting at the center of a coordinate system, okay, and it also has a watch or a clock by which the observer is measuring time. Okay. So, now you will see that the person will have some instruments to measure both distance and time. So, it can measure displacement, it can measure velocity, it can measure acceleration, everything. Okay. And now also it should know all these exterior things by virtue of its knowledge. That is, for example, if some force is acting on the particle, then what is that force? Okay. Again, some constant of the motion. So, intrinsic constants of the motion also should be known to the observer. For example, what will be the mass of the particle? Okay. If you know all these things, then you can finally or the observer can finally conclude definitively and quantitatively about the motion of the particle, and that is how a frame of reference acts. So, whenever we use this phrase frame of reference, it actually says a combination of an observer, a coordinate system, okay, and the observer is assumed to sit at the origin of that coordinate system, okay, and also the observer should have a watch, okay, or a clock to measure the time. Okay. So, Newton's first law basically says another information which is not that a priori, but it is somehow a little bit, how to say, if you think carefully about Newton's first law, it will be more and more prominent to you. Okay. So, you will see that whenever we say that unless some force is given to a particle, the particle will not change its state of motion, it actually also says that in order to conclude like that, the frame of reference who is concluding about this about the motion of the particle should also be free from any force. Okay. So, it simply says that, let us say, if I am seeing a particle on which some force is acting and the same force is also acting on me in the same direction, then although some force is acting on the particle's acceleration will be exactly the same as that of mine, given my initial displacement and velocity are the same as that of the particle, and I am the observer. I am sitting at the center of the coordinate axis of the reference frame. Then although the particle is moving and accelerating due to a force, but since that movement and is exactly same as that of mine, the relative motion will not be perceived by me, and that is why with respect to me the particle is actually at rest, but I know that some external force is acting on the particle from my knowledge. So, for me Newton's first law is not holding good, because force is acting on the particle and the particle is at rest with respect to me. And what is causing this whole problem? It is the force acting on me, and if some force is acting on me, that will not be within my knowledge. That is the main problem. So, for example, I am giving you another example by which you can connect the whole situation. Let us say I am having a problem of identifying the colors, okay. And I am now asking a person that what is the color of that object. Now, let us say the person has given me the correct answer, that is, this is green, and let us say I cannot distinguish between blue and green. Then I can say, oh no, you are wrong, okay, it is blue. On the other hand, let us say the person whom I am asking the question has also some problem in identifying the color, and the person has answered me it is blue. And although it is green actually, since her or his perception, color perception is matching with that of mine, I will be happy, I am saying yes, this is the correct answer. Although someone third person who is having no problem in color perception would say no, both of you are actually wrong, okay. So that is the point, that in order to adjudge that whether the person is giving me the correct answer or not about the color perception, I have to assure that I have a true perception of all colors correctly. Here also, in order to make sure that some particle is without force, the observer plus the coordinate system, the frame of reference should also be free from force, and this constitutes inertial frame of reference. Okay. So, inertial frame of reference is a combination of observer, coordinate system and clock, which is a frame of reference, okay, free of any net external force. Okay. Now, of course, although we can define in this way, it is actually practically difficult to make sure that whether there is really a force is acting or not. And for that we have to actually employ another frame of reference, which is a guaranteed inertial frame of reference. So, you see that the problem becomes that if I have to prove or show that some frame of reference is inertial, actually I have to use another frame of reference which is inertial. But you see operationally this is not a good idea, because every time you are trying to use a frame of reference which is inertial in order to define a frame of reference which is inertial. So, for the operational convenience, the best way is actually to define inertial frame of reference like this: frame of reference where the Newton's first law is valid. So, basically what is the solution then? So, the frame of reference and of course, the observer involved in that frame of reference, if the observer knows that no force from external agent is acting on the particle, and under that situation the particle is maintaining its zero velocity or some constant velocity forever, then that reference frame can be sure okay. So, with respect to me, a particle is actually moving in such a way that the Newton's first law is holding, and also the observer also should check that whenever there is a force, the particle is trying to change its velocity. Okay. If all these are true, then actually then the person or the observer can say okay, the reference frame attached to me is an inertial frame of reference. Okay. So, what is the basic advantage of defining reference frames? So, first is that if now you can of course gather all the reference frames which are inertial, that means who have Newton's first law to be valid in their reference frames for any arbitrary particle, and then if you study the motion of the particles, then they will always without any problem agree about the nature of the particle, whether the particle is force free or the particle is acted by a force. Okay. So, whenever we say that the concept of inertial frame of reference is necessary, that is necessary in order to first universally define a force free situation and a forced situation. Okay. So, that is something, and that is why we can say that a free particle remains a free particle in any inertial frame of reference, and a non-free particle, that means a particle on which some force is acting, remains so in any other inertial frame of reference. Okay. So, that is something for the sake of universality in the study of kinematics and dynamics. Now, coming to this point, that what is the most important advantage of defining all these things and this making Newton's first law valid, because if you see that if let us say you and your friend, both of you have some frames of reference attached to you, and now you want to compare your conclusions about the motion of the same particle. Okay. So, if for example, if you conclude in a way which is different from that of your friend, every time you have to make several complicated calculations in order to connect you and your friend. Okay. But if both of you know that you are inertial frames of reference, then you can always say, okay, for both of us the laws of physics are the same. Okay. And these laws of physics are the laws of Newton's. Okay. Now, the last thing here what I would like to mention is that can we, if we agree to the suggest to the proposition that okay, all the laws of physics should be unchanged, at least for classical mechanics should be unchanged from one inertial frame to the other, then can we propose some transformation rule for the coordinate system or for the coordinates, space coordinates and the time coordinates, such that finally the laws of physics are same. Then the first question comes, how would you specifically say what are the laws of physics? So, for us the first law of physics is, here in classical mechanics, is the law of Newton or the first two laws of Newton, and so the laws of dynamics. That means that for a particle of constant mass, you can say m d2x dt2 will be equal to m prime d2x prime dt prime 2. So, let us say in one frame of reference the distance or the displacement is x, I am just considering one dimension. Okay. So, in one frame of reference this is x, the time is t, the displacement is x, the time is t and the mass is m. In another frame of reference the mass is m prime, time is t prime and displacement is x prime. Now, if you remember that we just said that mass is constant, or we can actually sometimes even we can think of the mass can be more generally a function of time. So, in this whole business what we have to find is a law of transformation by which Newton's second law remains the same. That means this will be equal to this. Why? Because from our knowledge we know that the same external force F is acting on the particle. So, that external force being a vector should not depend on who is measuring this one. So, the force itself should be always the same. Okay. Now, who is measuring this, or which observer is measuring the force? According to that, its component about different directions can change, but the total vector should not change. In 1D, that is why it is both the vector and the magnitude should not change. Okay. So, we know that if we know that since both of them are claiming to be inertial frames of reference, then basically there should be an equivalence between this one to equal to f and also this one equal to f. Okay. So, this should be equal. So, what can be the laws of transformation which are consistent with that? For that, it is seen that if you make a transformation, the most general transformation possible is this. So, before you first have to, most general transformation means here what I am trying to say, that under the assumption that time and space, so time and space are not connected. So, this is an assumption. If this assumption is true, and that is called the concept of universal time and universal space of Newton. If you assume that, then the first thing comes is that for time you just have, you do not have different directions, you just have one possible direction. This is the direction of increasing the time. Okay. So, if you start from some point 0 in your watch the counting of time, and from the same time instant your friend is also starting counting the time, then after some times, okay, both of you again, if you stop simultaneously, both of you should measure the same time. So, that is why t should be equal to t prime. If t should be equal to t prime, one can actually show, this is quite easy to understand, that the basic for laws of physics to be same, laws of physics means Newton's laws. Okay. To be same in both frames and actually in all inertial frames, okay, we have to have now d2x dt2 times m is equal to m prime d2x prime dt prime 2. We have already argued why t and t prime should be equal, since t is equal to t prime, that is the concept of absolute space and time. So, once again the concept of absolute space and time says that the space and time they are not related, not connected. Okay. So, the space and time they are independent, and the space can of course change as a function of time. I mean the space coordinates can change for a particle when it moves, okay, but space itself is totally independent of time, and both are actually absolute by themselves. Okay. For space you have, according to the dimension of the problem, you have some number of directions for the space. For example, for a 3D space you have 3 independent directions. For time you always have one direction, which is the direction of the increase of time. Okay. So, if you have such thing t is equal to t prime, you can actually say mass, which can be most in the most general case as a function of time, which we said is also constant. Okay. And this is also a good assumption, that mass is constant and mass is it works like a universal constant for a particle, constant scalar. So, m is equal to m prime, and then you actually have d2x dt2 is equal to d2x prime dt2, because t prime is equal to t. that you can write. Here you see that t prime has become t. Okay. So, if you now see this to be equal, then of course, you know that this x prime minus x d2 dt2 will be equal to 0, and that is why the final thing comes that your x prime minus x will be equal to, so d dt of x prime will be some constant, let us say u, capital U, this is a constant. Okay. So, this is d dt, this is a constant, and then you say okay, x minus x is equal to u t plus another constant, let us say I do not know, some x 0. Okay. You can always write that. So, if this is 0, then d dt of this is equal to some constant, and then this one will be actually a linear function of this. I can always choose this some initial displacement to be equal to 0, because this is just a constant. You can simply say that at t is equal to 0, x prime and x should be equal. That is easily achievable just by making the origins of these two coordinate axes corresponding to those two frames of reference at the initial time instant. Okay. If you make the origins of these two frames of reference, okay, coinciding with each other at t is equal to 0, then this x 0 is 0, and finally, you can say that x prime will be equal to x plus u t. Okay. Or you can simply say that x will be equal to x prime minus u t. You can now generalize for 3D. So, for 3D you will have actually x prime is equal to x minus u x t, y prime is equal to y minus u y t, and z prime is equal to z minus u z t. You see that these three constants, they are actually having the dimension of a velocity, and what they are. If you now think that okay, that you and your friend, you are not actually at rest with each other, but one of you is moving with a uniform speed with respect to the other, then also the laws of physics remain the same. And is this something which is surprising? No, of course, because you see that just like the one frame which is inertial, it should have no force. So, that frame actually can be at rest, or it can actually move with a constant speed. So, two inertial frames can actually have 0 relative speed between them or some constant relative speed between them. Okay. So, which is non-zero. So, here if you just consider this case along with this t prime is equal to t, this constitutes the most general case where two inertial frames of reference are connected. Okay. Now, if you go to this picture, you see this is exactly this thing where this one. So, let us say it is your friend who is moving with a velocity, let us say u, with respect to you here, and then you will have a transformation like this, okay, for the coordinates, space coordinates and the time coordinates. This set of transformation is known as Galilean transformation. And so, Galilean transformation constitutes the basic transformation of the space coordinates and the time coordinates, which are consistent with Newton's mechanics and Newton's idea of absolute space and time. Okay? Thank you very much.